let's go up here and click on this. And today we're on page 239, topic 5.1. I meant to send you an email and say read pages 228 to 238, but I didn't. So we'll just have to read it later if what we talk about in class doesn't make sense. On page 239, in problems 1 through 5, identify the underlined items as cardinal numbers, ordinal numbers, or identification. And another word for identification is nominal. Sometimes you'll see people talk about nominal. So cardinal, ordinal, and identification or nominal. You go, I don't know what those words mean. It's on page 230. Cardinal, that just sounds like a bird. Ordinal sounds like order, doesn't it? First, second, third, fourth, fifth, that kind of thing. And identification, do all of you have an identification number or numeral? You know the last four digits of your Social Security number? So we all have a number that's used for identification or a numeral that's used for identification. So if we identify ourselves with numerals, and then we can say first, second, third, fourth, fifth, then the next use of numbers would be how many? And that's called cardinal. Now you go, how do you get cardinal out of how many? How many cards in a deck of cards? Anyone know? 52. So there, 52 is how many? And cardinal sounds like cards. So 52 cards in a deck. A cardinal would tell you how many. You understand? I'm trying to help you figure out someplace in your mind where you can hang these words and connect them to concepts. So with that in mind, if my telephone number is 816-331-8607, what is that number? Is that cardinal, ordinal, or identification?
Identification.
Because it's your phone number. It identifies the number that I use to call you on the phone. You follow that? So number 2, this is the second problem in this exercise. Now that can get a little tricky, but think about it. This is the second problem, so as soon as I said second, that would be like second, third, fourth, fifth. When you put that TH on it, what does that tell you?
It's an order.
It's an order, so that would be the ordinal use of the numeral. And then 3, it takes 2 to tango, whatever that means. But watch what you could say. How many does it take to tango? And the answer is what? 2. So what would 2 be in problem 3? What? Cardinal. Right, cardinal. Why am I doing your problems? I don't know why. I guess I missed this stuff so much, I just want to keep working it. Problem 4. Now, this is kind of tricky too. 1, 2, 3, go. Is that kind of like on your mark, get set, go? So what would that be? First you get on your mark, then you get set, then they, boom, shoot the gun and you go. So that would be ordinal. Number 6. There are 3 numbers circled on this check. Have all of you seen a check? The world is changing because we don't see checks anymore. It's just automatic deposits and pieces of entries on a statement. Well, your grandparents paid all their bills with checks. When my grandfather died, we were going through the house cleaning things out. I found a box with all the checks he'd ever written, all of his canceled checks. And I just sat there one day going through them, and I found one that he had written to me when I was a little kid for working for him in the field, and I'm going, whoa, I think this was my first paycheck. And he had saved it in a box, and I was just reading through them to see what he spent his money on, how much he paid for feed and stuff like that, and for other things he bought. So it's kind of fun. If you ever find a box of your great-grandparents or grandparents' checks, you can learn a lot about your family by just reading those old canceled checks. There are 3 numbers on this check that are circled: 14, 5696, and 0166. So, what do you think 14 is?
Ordinal.
Yep, ordinal. Because it's the 14th check. The 13th, 14th, 15th. What do you think 5696 is? What is 5696? It's how much the check is written for. So what would that make it?
Cardinal.
Cardinal. Cardinal is how much? And then what would 0166 be? Have you ever looked at your checks? What is that on your check? Those last digits after that?
Account number.
That's your account number. If you didn't know that with a check, the first numbers up there have to do with the identification for the bank, and then that's how those last digits identify your account number. So that would be identification or naming, which is also nominal. Okay. Any questions on 1 through 6? Is it clear in your mind, or do you need to write some notes to keep it clear so when it comes test time, you can tell the difference between cardinal, ordinal, and identification? 8 to 11. Prime and composite. The first thing it tells you to do is continue the sieve of Aristophanes on page 231 and find all the prime numbers between 50 and 100. Well, I saved you all the grief. See that little thing on your table? Look what I gave you. A prime number chart that goes way beyond 100, clear up to 997. And if you want one that goes further than that, just get on the internet and Google prime number chart, and you'll find. So I've already done problem 7 for you. What a way to start math after we come back from spring break. So we're going to use this chart to answer the questions in 8 to 11. Number 8, find in problems 8 to 11, use the results, this little chart, and find how many prime numbers there are between 1 and 25. So I look on this chart for 1. It's not there. Why isn't 1 there? It's not a prime number. And neither is 25. But what are the prime numbers between 1 and 25? Just say them out loud. 2, 3,
5, 7, 11, 13, 17, 19, 23.
That's it. That's all you're doing is looking at the chart, and this chart's got the prime numbers there. You go, why are they prime numbers? Does anyone know the definition of a prime number?
A number that is only divisible by 1 in itself.
Thank you very much. And for those who don't know that, you can go back and read about it in the 10 pages that I didn't tell you to read. because you were still on spring break. So you can go read it and find out. That's what a prime number is. Oh, it says that right on the handout, doesn't it? We're making it easy today, aren't we? Got to get our brains back in math mode. Number 10, the prime numbers between 50 and 75. 50 to 75. What are the prime numbers? Say them out loud.
53, 59, 61, 67, 71, 73.
There you go. Question 12. Refer to the chart and find the smallest prime number. What's the smallest prime number on this chart? 2. An even number.
2.
2. Is that the only even number on this chart? Yeah, you know why you know that? If there was another even number on the chart, you could divide that number by 2. Agreed? So that number wouldn't be a prime number, because prime numbers are only divisible by 1 in themselves. So 2 is the only even prime number. Just thought you'd like to know that. We're just moving right along here, aren't we? Prime numbers that differ by 2 are called twin primes. The smallest twin primes are 3 and 5. See how you look on this chart and it says, oh, there's from 2 to 3 is 1, from 3 to 5 is 2. So find 2 other pairs of twin primes. Oh, well, I missed one. Wonder why I didn't circle that one. So 3 and 5 are twin primes. What's another set? 5 and 7. You see that? They differ by 2. Then keep going across there. 17 and 19. And then keep going across. 41 and 43. There's a whole bunch of them. Skip problem 15. And let's go to problem 16. In problem 16 to 21, find all the factors. What's a factor? It's all the numbers that will divide into 28. Well, we already know 2 of them, don't we? 1 and 28. So when you make your list, don't forget to list 1 and 28. But what else can I divide into 28 besides 1? 2. Can I divide 3? Evenly. Factors have to divide evenly. No, 3 nines is 27. So you've got a remainder of 1. So, but I could do 4. Now, and watch what happens when you're looking for these factors, and these are called factors. When you're looking for these factors, 1 and 28, 1 times 28, 2 times what is 28? 2 and 14, you see that? Because 2 times 14, so 14 is also a factor. And 4 times 7. See what's going on? And then it's like, are there any other numbers that are factors of 28? You go 5, 6, 8. You go, 8 looks like it'd work. Well, 8 into 28 would be what? 24 with the 4 remainder. You follow what happens? You just keep checking them out till you find all the factors. And you want to find all of them. Okay? So 28 is pretty easy. Let's go to problem 18 and work 119. Well, I know 1 and 119 are going to work. But then what else? 2, 3. Maybe we just need to get our little calculator out. If your mind's just not very eager to do math today, and just go 119, let's see, divided by 2. Oh, I hit times. What's that all about? 119 divided by 2. Nope, it came out 59.5. So you see, if I get a decimal point, it doesn't come out even. Then divide by 3. 39.666. No, see what I'm doing? I'm just taking 119 and looking for all the factors. 4. You go, no, 4 is not going to work. And if you don't know, just go 119 divide by 4. And just keep messing around with them till you find them all. And 6 looks like it would work, but it doesn't. 7 does. It does. You go 119 divided by 7. Yeah, it equals 17. So I put 7 and 17 here. And then after I keep messing around with my calculator for another 5 or 6 minutes, what do I determine? Those are the prime factors right there. That's all there are. Those 4 and no more. 22 to 27. Find the prime factorization for 24. Okay. What are 2 factors of 24? 4 and 6, right? Or 2 and 12, or 3 and 8. Everybody follow what I'm doing? In other words, in the past I found that people go, well, how do you find the right 2 numbers? It doesn't matter. If you get factors, you'll eventually end up, all of these factorizations end up at the same place. So we get the same answer no matter how we break it down. Because here for 4 and 6, then 4 breaks down to 2 and 2 and 2 and 3. 2 times 2 and 2 times 3. This is called a factor tree. Have you made these before anywhere in life? Okay, some of you have and some of you haven't. For those who have, you go, okay, this is just a review. For those who haven't, it's new stuff. 2 times 12, I bring down the 2 again, and 12 is 3 times 4. Or it could be 2 times 6. You see, you've got, but it doesn't matter which way you do it. You're going to end up at the same place down here at 2 times 3 times 2 times 2. 2 times 3 times 2 times 2. You're going to have, another way to write this is 2 to the 3rd times 3. 2 to the 3rd times 3. And this is 2 to the 3rd power times 3. So you get the same answer no matter how you build your tree. So what were we supposed to do for problem 22? Find the prime factorization. We just did. There's the prime factorization. 2 to the 3rd times 3, because I factored it down to prime numbers. Numbers that are on my prime number chart. Let's do problem 24. 82. Well, I see it ends in 2, so I go 2 and 41. And look at your chart. This is what's handy about keeping this chart handy. You go, can I break down 41? Is 41 on this chart? Then 41 is the prime number, so you can't. So you're done with it. The prime factorization is 2 times 41. For 82. You go, I'm thinking, can't you divide 4 into 82? You're going to get 20 with a remainder of 2. You follow what's happening? So it's not going to come out even except with 2 and 41. 26, 191. Don't you hate it when they give you a problem and say factor and you can't factor it? Because when you look at your chart, you go, 191 is on the chart. So it's a prime number. So it's just 1 and 191. Any questions on building these trees? And by the way, when you're working these problems, that's how you show your work. You build these trees, and I see your work. You build these trees to get these prime factorizations. 28. Find a natural number whose prime factorization is given. Two times 3 squared is 9, times 5 squared is 25. So that's 50 times 9, 450. So you're just going the other direction. I mean, this if it was written out, it would be 2.3.3.5.5. In other words, if we took 450 and built a tree, we would end up with 2 times 2.3.3.5.5. You follow that? And they just want you to take this prime factorization and find the natural number that it came from. Number 30. 2.3.5.11. Well, how did I get 30? Oh, 2 times 3 times 5. 30 times 11 is 330. Or I took 2 times 5, 10, and 3 times 11, 33, and get the same answer. But you understand, we don't have to all get there the exact same way. When you're multiplying these numbers, you can mix them up in terms of how you multiply them. All right. So that takes care of up to question 30. In problems 32 and 33, determine whether each number is divisible. Is this number divisible by 2, by 3, or by 5? Do any of you remember learning how to check if a number is divisible by 2? Well, if you don't remember, the rules for divisibility are on page 233, and you ought to write them down and keep them in your notes. It's divisible by 2 if it ends in what?
An even number.
An even number. It's divisible by 5 if it ends in a
5 or 0.
5 or 0. It's divisible by 3. Oh, did you memorize that rule? Did anybody memorize that rule? See what happens? 468. I add 4 and 6 and 8, and I get 18. Is 18 divisible by 3? Yes. So if the sum of the digits is divisible by 3, then I say, yes, it's divisible by 3. Yes, it's divisible by 2. No, it's not divisible by 5. You follow what's going on? Let's do 580. Divisible by 2? Yes. Divisible by 3? I don't know. Add 5 and 8 and 0 and you get 13. Is 13 divisible by 3? No. So it's not divisible by 3. Divisible by 5? If it ends in what? 5 or 0. So yes, it's divisible by 5. 795? Divisible by 2? It has to end in an even number to be divisible by 2. So no, it's not. Divisible by 3? Well, let's add them up. 7, 9, and 5 add up to 21. Is 21 divisible by 3? Yes. So that number is divisible by 3. Is it divisible by 5? It ends in a 5 or a 0, so yes. Follow what's going on? So if you don't know the divisibility rules, just turn back to, what page did I say it was on? To page 233. And you don't have to copy it down verbatim from the book. Just read what it says and think about what we just did in class and write down a definition that makes sense in your head that you can use when it comes time for the test. All right, we're ready for 34. Find the smallest whole number, multiple of 4, that leaves a remainder of 1 when divided by either 5 or 7. Well, here's how I work that problem. Multiples of 4. I just made a list of multiples of 4. 4, 8, 12, 16, 20, 24. Does everybody understand? This is 4 times 1, 4 times 2, 4 times 3, 4 times 4, 4 times 5. But that's the same as just adding 4 to each answer to get the next number. So I just kept going up here. How come I stopped at 40? Oh, because it leaves a remainder of 1 when divided by 5. When you divide by 5 or by 7. So let's divide by 5. 4 divided by 5 is 0, remainder 4. 8 divided by 5 is 1, remainder 3. 12 divided by 5 is 2, remainder 2. 16 divided by 5 is 3, remainder 1. Aha, I got a remainder of 1 here. You follow that? But when I come down here and start doing divide by 7, 4 divided by 7 is 0, remainder 4. 8 divided by 7 is 1, remainder 1. I got a 1 here, but I have to get it both places. So I keep going with the 7s till I get out here to this one. And then I come up here and check the 3, and 3 into 35, sorry, not 3, 5. 5 into 36 is 7, remainder 1. So there's the answer to the question. What number, what multiple of 4 leaves a remainder of 1 when divided by 5 or 7? Wasn't that fun? I just had so much fun writing all this stuff out on paper. And I'm looking at some of your faces, and I can see you're thinking, I don't know what they're asking, but it looks like too much work. Who cares anyway? I do. I just want to know this stuff. I'm sorry if you don't have as much fun with it as I do, but hey, you know, but you follow what you do? When you see something, say, I can take what they've given me and just write this stuff out and run through the process. And of course, you don't have a little tablet like this to work on, because this is so cool. I mean, if it would have gone out 100 places, I could just keep scrolling over and writing till I found it. But it didn't go that far. I found it when I got to 36. And I just kept checking every one of them. You go, who would go to that much trouble? Have you ever gone to a thrift store and seen a briefcase or a suitcase that was locked? And since it couldn't be opened, the thrift store was selling it for 50 cents. And it's like a $50 briefcase. I buy those. There's only 3 dials on it, okay? And the dials go from 0 through 9. So have you figured this out? 9 times 9 times 9 is what? 729. All I have to do is sit there in my little easy chair and just try 0, 0, 0, 0, 0, 1, and just do that 729 times, and the thing pops open, and I have a $50 briefcase for $5 because the people at the store didn't know how to open it. You go, who wants to waste that much time for a $50 briefcase? How long do you, okay, I've never had to dial all 729 options. I usually find it either a third or a half of the way through. Sometimes I have to go 3/4 of the way through. And then my grandson gave me a padlock with 5 wheels on it. My thumbs were sore, and I wasn't even getting close to finding it. And I gave it back to him, and I said, you know, this isn't going to work, bud. It's going to take too much time. He goes to the internet and finds a website that shows him how to use a feeler gauge. It's a little tool for checking the valve lifters on a car. Shows him how to stick a feeler gauge in the side of it and disengage the mechanism and opens the lock. Kid's a freshman in high school, and I have a PhD. How embarrassing. I'm sitting there dialing the numbers, and he just works through it. Good for him. But I like doing stuff like that, so it's no big deal. So if you see a briefcase for 50 cents and you don't want to mess with the dials, go ahead and buy it, bring it to class. I'll pay you 50 cents for it, and then I'll open it. 36 to 45. Okay, now we're doing greatest common factor and greatest common factor and least common multiple. You need to learn the difference between those two. So 36 says, in problems 36 to 45, find the greatest common factor. Here's how you find the greatest common factor. The greatest common factor, I'm going to change colors here, for 14 and 210. Okay, I make a tree for 14 and I get 2 and 7. I make a tree for 210 and I get 7 and 2 and 3 and 5. Everybody see that? So now, what's common to both of these? A 2, see that? There's a 2 in each one, and there's a 7 in each one. So 2 and 7 are my common factors. So the greatest common factor is 2 times 7, which would be what? 14. Everybody see that? Now, if I wanted the least common multiple, just to show you the contrast here, if I wanted the least common multiple, okay, multiples of 14, I could just list them all out here. 14, 28, 42, 56, and see, I could just keep listing them out. And then I could take 210 and list out 210, 420, 630, what would the next one be? 840. And I keep going out here till I keep making them till I find the one that matches. And there's 210, and here's 210. So the least common multiple of 14 and 210 is, now watch how I can find it without making that list of numbers. It has to have a 2, I'll change to green here. It has to have a 2 and a 7 in it, so I put a 2 and a 7. So that takes care of the 2 and the 7. So now I have to have a 3 and a 5. So I put in a 3 and a 5. In other words, I want this least common multiple is a box that has to contain both numbers with the least number of prime factors. That's the difference between the least common multiple and the greatest common factor. And I think what confuses people, when you say greatest, you go, well, this number is greater than this one, than 14. 210 is greater than 14, but we're not looking for the greatest number. We're looking for the greatest common factor. We're looking for factors of these two numbers and which factor would be the greatest common factor. And then least common multiple, now we're looking at multiples of the numbers, and we're looking for the smallest number that's a multiple of both of them. Well, let's do number 38. 315 and 350. I make a tree, and I come up with 3, 5, 3, 7, and 5, 7, 5, 2. So what's common? I've got a 5 from both of them, so I put a 5 in there, and I have a 7 from both of them, so I put a 7 in there. You see, I don't have the 3s, and I don't have the 2, and I don't have another 5. You follow what's happening? I'm looking, so here's another way to look at it. Okay, there's no 3, there's a 3 here, but no 3 here. There's a 5 here, and there's a 5 here. There's a 3, but no 3. There's a 7, and there's a 7. So those are the greatest common factors. Does that help make sense to it? To what's going on there? So the greatest common factor is 5 times 7, which is 35. Okay? Now, what if I wanted the least common multiple? Well, the least common multiple, let's change to blue since we're working with these numbers, colors here. So the least common multiple, it has to have a 3 in it, has to have a 5 in it, has to have another 3 in it, and it has to have a 7 in it. So I've got the 5. You see that? I've got a 5 in there. I've got a 7 in there. I need another 5. And I need a 2. See what I've done? Now I've put in this box, I've put enough factors in here to include 3, 5, 3, 7, 3, 5, 3, 7, and 5, 7, 5, 2, 5, 7, 5, 2. So I've got the smallest number of factors that include both 315 and 350. And what number is that? What's 3 times 3? 9 times 5, 45 times 10, 450. What's 450 times 7? 3,150. There's the least common multiple of 315 and 350. And here's the greatest common factor, 35. See what's going on? So that takes care of, do we do 42? Yeah, we might as well. 12, 18, and 30. So I make a tree, and then after I get my tree done, I go for, okay, what do I have here? I have a 2, and a 2, and a 2, and I have a 3, and a 3, and a 3. Anything else that's common to all 3 of them? So that's it. 2 times 3 is 6. So the greatest common factor is 6. And if I wanted to do a multiple, I need 2 and 2 and 3. So there's 2 and 2 and 3. Then I need 2 and 3 and 3. There's 2 and 3 and 3. And then I need 2 and 3 and 5. There's 2 and 3 and 5. So I already have the 2 and the 3 there. I just need to add the 5. And then what does 2 times 2 times 3 times 3 times 5 come up to be? Well, 3 times 3 is 9, times 5 is 45. 45 times 4 is 180. Okay? What's number 46 say? Oh, I'm working on 46 is I've got this fraction. 46 says reduce each fraction. So watch how I reduce fractions. I make a tree. From 80 I go up, and then these are my prime factorizations. And from 92 I go down, and these are my prime factorizations. And then what do I do next? I cancel out. 2 over 2 is 1. 2 over 2 is 1. So what am I left with? 2 times 2 times 5 over 2 over 23. What's 2 times 2 times 5? 20. So the answer is 20 over 23. Is that a cool way to reduce fractions? Is make a tree going up, make a tree going down, and then once you get your prime factorizations, cancel them out. And this is the kind of stuff you show on your paper when you're showing your homework. Do I have another one of these? Yeah, number 50. 315 over 420. Let's reduce that down. I make a tree, and I get 5.7.3.3. Then I make a tree down here, and I get 5.2.2.3.7. And what can I cancel out? A 5 and a 5. No 2's, no 2's. A 3 and a 3. And a 7 and a 7. You follow what I just did? So what's left? 3 up here and 2 times 2 down here. So what's the answer? 3/4 when it's reduced down. Just that quick. You can reduce fractions. Why didn't someone teach you about these trees? Or did someone teach you about using trees to reduce fractions when you were in school earlier in life? Well, if they didn't, send them an email and say, shame on you. I just learned a cool little way to reduce fractions that's stress-free. What's number 53 tell us to do? Find the least common multiple and add the fractions. Well, 15 factors into 3 times 5, 55, 5 times 11, so the least common multiple is going to be 3 times 5 times 11. So 1 over 15 is going to be, so this fraction is going to become this fraction. Well, 15 is 3 times 5, so that means I have to take this times 11 and times 11. So that means that's going to be 11 over whatever this comes out to be. 15 times 11 is what? 165? But I'm not going to work it yet because I'm going to save that for later. So 55 becomes what over, and see 55 is 5 times 11, so I have to take this times 3 and times 3, so I have 3 here. So my answer is 14 over 3.5.11. And the reason I haven't worked it yet is 14 is 2.7. You follow that? And the reason I do that is, can I cancel out anything between the 2 and the 7 and the 3, 5, and 11? Nope. So I know my final answer is going to be 14 over, what did we say? 165. And I know by looking at this tree, by looking at these prime factorizations, I have it in lowest terms. Number 60. 1/12, 1/15, and 1/20. So I take 12 and get this, 15 get this, and 20 and get this. So my least common multiple has to have 3 and 2 and 2 in it, has to have 3 and 5 in it, has to have 2 and 2 and 5 in it. See what's happened? I have to, in this box, I have to have all 3 of those numbers without any extras. I don't want extra numbers in there. So now my new denominator is 3 times 2 times 2 times 5. But 12 is 3 times 2 times 2. So I just need to put the 5 out here. So this becomes 5. 5 times 1. Now, what I don't like about this exercise that it gives you is that it always uses 1 for a numerator. If that was 5 twelfths, then it would be 5 times 5 is 25. You follow that? So when you take this technique and use it someplace else, you won't always have just 1 up above. And then 15 is 3 times 5. So that means I have to take 4 times 15 and 4 times 1. So this is 4. And then 20 is 4 times 5. So I take this times 3 and this times 3. So I end up with 5 plus 4 plus 3, 12. So now watch what happens. I end up with 12 over 3.2.2.5. And 12 is 2 times 2 times 3. Everybody see that? So, wow, look what that happens. Look what happens now. So this, change colors, this cancels here, this cancels here, this cancels here, and I'm left with what? 1 over 5. 1/5 is my final answer. Okay? Let's see. Question 64. Let's do, okay, stop when you get to 69 so you know how far you're going. But let's do a couple of these story problems. 64 says, in a recent year, 1,035 billion dollars was spent on health care in the USA. And of this amount, 1/10 was spent on drugs, eye care, and something else. 1/4 was spent on professional services. 2/25 was spent on nursing homes, and 3/20 was spent on miscellaneous, and the rest was spent on health care. I guess I could put the rest down here. But I don't know what the rest is. But if I change these to a common denominator, which is hundreds, 10 over 100, 25 over 100, 8 over 100, 15 over 100, and I add those up, I get 35, 43, 58. So I get 58 over 100, and if I subtract that from 100 over 100, that will tell me how much the rest was. 42 over 100. Or 21 over 50 if you reduce it down. So whenever you see a problem that says the rest and they give you a bunch of information, that means you add all of these together and subtract them from 1 to find the answer. Number 66. A bookstore owner spent 3/5. So here's 3/5 on bookcases. 1/10 on office machines, and the rest on books. So I go 3/5 is 6/10, and 1/10 adds up to 7/10. So how much would the rest be? 10/10 minus 7/10 would be 3/10 would be the rest. You follow what's going on? It's the same process over and over again. When you see a story problem that says, so this and this and this, and the rest was spent here, well, all total makes one whole. So then you say, then I just take the number 1 and make a fraction out of it, 10 over 10, 100 over 100, whatever the common denominator is for my parts, and I find the answer. Number 68. You know what's in your trash? It says 1/5 is yard waste. See how you take all these words and pull this stuff out of here? 1/10 is what? Food waste. That's disgusting. 1/4 is what? Wood. Oops. 1/4 is metal, glass, and plastic. And 1/8. And 1/8 is wood, rubber, and miscellaneous. So what's my common denominator for 5, 10, 4, and 8? 40? So that would be times 5 times 10 times 4 and times 8. So I add those numbers together, change colors here. 8 and 4 and 10 and 5 add up to what? 12, 22, 27 over 40. And I subtract that from 40 over 40. And what do I get for the rest? $13 over 40. Is that a cool problem-solving technique? To just take all those words and extract the stuff that they're telling you, and then put down the rest, and then just get a common denominator, add them all up, and subtract them from 1. Or a fraction equivalent to 1. Well, there you go. Are you feeling exhilarated, or is there kind of a sickening feeling in the pit of your stomach that says spring break was much better than this? Welcome back. We're going to do math for a few more weeks. Okay, like I said, stop at 69.